Here we're going to look at question 14, where we have a function that takes in a velocity v, or a speed v, where the function returns the gas consumption in liters per kilometer of a car. And so the idea is, depending on how fast you're driving, you get different gas consumption. We're told here that when we're going at 80 kilometers per hour, we are consuming 0.05 liters per kilometer. And more interestingly, when we look at this prime value, when we're at 80 kilometers per hour, so we're traveling at slow highway speeds, we have a rate of change. Again, here I have to be careful. This is in liters per kilometer. Those are the units of F. In fact, it might be better to write this as dF dV. The units of F are in liters per kilometer, they're the gas mileage. But then we ask, how does that change as we change our speed of the car? This in words would translate to, when we're traveling at 80 kilometers an hour, when we're at 80 kilometers per hour, each increase of 1 kilometer per hour will increase our gas consumption by 0.0005 liters per kilometer. In other words, increasing our speed will increase our consumption, which is not news for most folks. The faster you go, and once you're at highway speeds, the faster you go, the quicker you're going to burn through gas, but also the faster you're going to get there. There's going to be some trade-offs to that. The follow-up questions are going to involve little transformations of that derivative to cast the rates in slightly different ways. Let's take a look. Here are the statements we had earlier, simply translated into words and with the units expelled out. Now we're going to define a new function, g of v, be the distance the same car goes on 1 liter of gas at velocity v. So the same input, but now g is equal to the distance, kilometers, per liter of gas. First up, what is the relationship between f and g? Well, f is the liters per single kilometer, g is the kilometers per single liter, so g of v is just 1 over f at that same velocity. For example, since f at 80 is equal to 0.05 liters per kilometer, or every liter gets me 1/20th of a liter is what it takes per kilometer distance. G of 80, so if we're traveling at 80 kilometers an hour again, but we want to look at it the other way around, we're going to end up with 20 kilometers per liter. And some people like this expression. This is kind of like the miles per gallon unit used in the States. How far do I go for each liter of gas that I have? Again, conditional on going at 80 kilometers per hour. What's also interesting is if we look at g prime of 80, and we can calculate that, starting with this relationship here, we can take the derivative of both sides and get g prime of v, which is going to be the derivative of 1 over f of v, or 1 over f of v squared, times f prime of v from the chain rule. This is f of v to the negative 1, so we get negative 1, that to the negative 2, times the derivative. If we fill in the blanks, we're going to have negative 0.0005 over 0.05 squared. And the key expression for that is, again, the units. This is going to be how the kilometers per liter changes per kilometer per hour. So for every kilometer per hour we go faster than 80, it's important we should put an 80 in here. G prime of 80 is equal to this. We're going to go fewer kilometers on each liter because our gas efficiency has just gone down a little bit. Perfect. If we calculate this as a specific value, we end up with negative 0.2 kilometers per liter. For every kilometer per hour we go faster. We lose that efficiency for every kilometer per hour we go faster. We don't have to limit ourselves to that. We can also look at something else like H&V, which is the car's gas consumption in liters per hour. So if we drive for 1 hour, how much gas do we go through? Well, first off, we have to figure out how that new thing, H, which is in liters per hour, how that relates back to F. And F, remember, is liters per kilometer. And so the thing we might have to combine here to get liters per hour is, well, we need the cancellation of the kilometers, and we need hours in the denominator, so that's that. Oh, what? Hey, hold on, there we go. If we multiply by the velocity, we're going to get the consumption in liters per hour. So how quickly are we burning through our fuel? The units make total sense here. This is how many liters we go on each, or how many liters it takes to go for each kilometer. And we're going to be going through those kilometers more or less quickly depending on our current speed. What that means is we can also do a nice simple calculation for the derivative this time. The derivative of this consumption rate is going to be a product rule calculation. We're going to have the derivative of the first times the second plus the first times the v derivative. V is our variable. So the derivative is going to be 1 for that second term. And we would typically write this as v times f prime of v plus f of v. And the units of that would be in liters per hour per kilometer per hour. How does our gas consumption on an hourly basis change as we increase our speed? And we can get that more specifically at the point 80 kilometers per hour at that speed. What happens when we change our speed a little bit? Well, it's going to be 80 times the derivative of f plus the value of f there, 0.05. Not too surprisingly, when we look at this, we see something positive, which says the faster we go, the bigger our v, the more gas we're going to consume every hour, because we're just being less efficient. We're also going to go further, but it's going to take more gas. At the end of the day, we end up with 0.09 more liters per hour for every kilometer per hour we go faster. Finally, how would we explain the practical meaning of these values, of these functions and their derivatives to a driver who doesn't know calculus? Honestly, while these might seem a little abstruse, these numbers that we're getting, if you say them in the sentence, we are going to go through or burn 0.09 liters more each hour for every 1 kilometer an hour we go faster or we go above 80 kilometers per hour. So if we cruise at 80 kilometers per hour, we know how our gas is being consumed. If we increase it by a little bit, 1 kilometer per hour or 2 or 3, this is going to be the multiplier effect. This 0.09 is going to cost us, or that's going to be how many more liters we're going to use every hour as we drive at those higher speeds. And correspondingly, that's how much we'd save if we went a little bit slower. But those kinds of sentences are the kinds of things that are typically used in both media, newspaper, and also technical reports to capture that kind of information without stating it with calculus.